In this video, I'm going to tackle bounded area in terms of x and y, volumes of revolution in terms of x and y, rotating around axes and around different constants. We'll get some practice with that. Also going to introduce the mechanical way of deriving the derivative of arcsin of x. We'll do it mechanically, get some memorization started there. And also we'll look at some inverse situations, so we'll get a function that you can't find the inverse for, or certainly not sure what it is, and yet you can find its inverse derivative values on occasion. And I'm a big fan of repetition, so doing this instead of a long, lengthy 50-question worksheet, these are some of the later topics. So you've been doing derivative of polynomials and things like that since lesson 1, but you weren't doing these then because it takes time to develop concept and some mechanics that you can build off of. And yet I want you to get a decent amount of repetition to put this in your longer term memory. So we're going to do a couple of problems here and talk about these again. So bounded area and volume of revolution, get a mantra going. And your mantra should be in terms of x, top minus bottom, left to right. For the most part, top minus bottom, left to right. Top minus bottom, left to right. So I gave you y equals 3x, y equals x squared, and the bounded area in the first quadrant. So if we draw that, let me draw it over here. We have x squared, we have 3x, and we want to create slices, altitudinal slices between the two functions. 3x, x squared, and I said top minus bottom. I hope you can see why now. That altitude comes from, give me an x value in the interval of where the area can be drawn, which is from 0 to 3. This is the coordinate 3, 9, but we're looking left to right. That's the right-hand border. They intersect at 0, 0. That's the left-hand border. So left to right would be 0 to 3. Top minus bottom is 3x minus x squared. We want to give each of those. So I'm really looking at 3x squared is that height. X squared, I'm taking away the x squared height. So I have the trapped altitude between the two functions. And so therefore, I've got to distribute the width to both of those altitudes. And that's the bounded area, and that's all we're going to do is just the calculation. Now, what if I wanted to rotate this around the x-axis? Well, that means I've got a big R. And in this case, it's still top minus bottom. Now, what's the bottom? The axis, which is y equals 0. So I really have 3x minus 0. You wouldn't have to write the 0, but I am right now. And then I'm going to get a picture that looks like this because I'm rotating this area around the x-axis. And so now I need to take away a smaller disk. So this is really this is going to be a bigger disk with a pi r squared. All right. So that's my big radius. My little radius is x squared minus 0. Because we're going to be picking different constants to rotate around. Then I've got to get little r squared. I've got to subtract one big disk from one smaller disk. Subtract one smaller from one bigger, excuse me. And I've got to give those radii some width from 0 to 3. All right, there's a little practice. Hopefully I'm saying things slowly enough at this stage that you have a chance to maybe see what's happening. Now what happens if I rotate this around y equals 10? If I rotate this around y equals 10, I've got to find my big R and my little r. Well, in this case, I can't, it's still a top minus bottom, but there's two of them. And the outside edge is going to be x squared in this case. So that's my big R. My little r connects to 3x. And I'm rotating around the axis y equals 10. And I want to see how much volume gets carved out. Well, so it's really pi, left to right still, big R squared minus little r squared dr. And dr in this case is dx. So what is this long distance? Well, I need to know what that x squared value is. I know the whole distance from 10 to 0 is 10, but I got to take away that little x squared aspect of the calculation. So I write what I say. 10 minus x squared gives me the length of my big R. I have to square that. 10 minus 3x gives me my length of my little r. I have to square that, and I have to distribute the widths to each of those situations. And that's rotating around y equals 10. Now what happens if I want to rotate around y equals negative 10? Y equals negative 10. Unfortunately, the picture works because I've got 9 units and change coming from x squared and 3 times x. So now, everything's the same here except I have to look at what my lengths are. What's my big R? Well, if I'm rotating from here, I'm going all the way up to 3x. That's the outside border. So it's 10 plus 3x is my big R. That's my big length. My smaller length is connecting to x squared. So I have to have 10 plus x squared. Well, that's how you do those. Now, there's plenty of practice on YouTube. Right? And there are probably better graphics. I'm sure a computer showing the graphics here will help you. So, go look at a few. But I'll keep giving you some on the, next 10 lesson sets, and then I'm probably done. It's going to take fewer lesson sets than I thought to cover the material that I want to cover with you. There's certain material that I don't think I can cover on this board because it's too flimsy, and I don't think it's going to come out too well. So, we'll see. Let's do the same problem now, but let's find the area bounded by those curves in terms of y. And I think the mantra should be right minus left. Right? If you look at an x distance now, not an altitude, but a side-to-side distance, if we're on a number line and this is 10 and this is 3, what's that distance? Right minus left. You know where you are on a number line, yes? You start at 0. So what's that long length if we're thinking like a big R? That long length is 10 units. What's the smaller length? That's 3 units. So what's the length between these? You're erasing the 3. That's why you say 10 minus 3. Sometimes you have to slow the brain down quite a bit to say, what did I do? So, our x is y divided by 3 because we're just looking at the first quadrant. Our y becomes the square root of y for that x. And now we can draw the picture, but we're going to talk about lower to upper, down to up. So those are your mantras. When you're doing it in terms of y, right minus left. When you're doing it in terms of limits, lower to upper. Okay, so 3x was now y divided by 3, and that hits an altitude of 9. Right? What's the square root of 9? 3 units. Right? And then this one was x squared. Now it's the square root of y. Okay, and what's the square root of 9? 3 units, because this intersects at 3, 9. But we're going to use what? Lower to upper. So we have an intersection at 0, 0. There's my lower y value, there's my upper. So we're going to use bounded area from 0 to 9. What is that x distance? It's right minus left in terms of y. And if you did that, you're going to get the same answer as you got the last time when you did it in terms of x. Throw it in a calculator or take the time to do it out, which is even better. Alrighty. Now, let's talk about rotating this around the y-axis. Okay, we're going to rotate around this way. then we need a big R. What's my big R? My big R is right minus left. What is this x value? This x value is 0. All right, so that's my border, and I'm trying to find x distances. So right minus left is the square root of y minus 0. That's my big R. I'm going to hit that at integration from 0 to 9, lower to upper. I got to get a pi, and I got to distribute my altitudes with a little bit of width. That gets me rectangular radius, which I rotate, which makes a disk, a horizontal disk. I've got my disks here. So there's a big horizontal disk, and then I got to take away a smaller disk, which is maybe the inside edge of the donut. I got to take that away. So what is little r? Little r looks to be y over 3 minus 0. What do I have to do to that to get pi r squared? I got the pi, I got the r, I got a square. And I take away the smaller disk volume from the bigger disk volume, and that tells me the volume of the revolution. Go Che. Oh, go Minutemen. Now let's do rotate around x equals 10. So x equals 10 is out here. Boom, 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 boom. So what's my big R? My big R is the longer radius, the connection, the string. I'm going to rotate that piece of string around. So how do I define that distance? Sure looks like it's 10 minus y over 3. So if y was 9, 9 divided by 3, I'd take 3 units away from 10. Must have been a Freudian slip before, because I did show 10 minus 3. So that's my big R. What's my little r? I'm connecting that length. Well, I'm taking 10 away. I'm taking the square root of y away from 10 to give me those readings. I've got to have pi r squared. So I've got to bring the pi out. I'm going from 0 to 9. I've got to subtract. I've got to distribute. Little changes in y, like from 2 to 2.01. And then from 2.01, I got to go to 2.02. And I said exactly the same number of decimals. So that's your revolution. Now let's go around x equals negative 10. Let's rewrite this as I... Notice we're doing the same thing each and every time, so I'm hoping you're getting some practice here. So instead of x equals 10, we'll come over to this side, and we'll go rotate that around x equals negative 10. So what's my big R? Looks like I'm going all the way across to the square root of y. Oh, but you know, I got some distance here. I know the square root of y is that distance, but I also have to do what? Oh, I got to add 10 units. That's my big R. What's my little r? Well, there's 10 plus y over 3. 10 plus y over 3. What do I have to do? Got to subtract. Give it a little bit of width, each altitude, a little bit of width. Got to do pi. Got to go from 0 to 9. And that's going to rotate around this, which means that I'm way over here. Way over here, I'm going to get something that looks like this. Woof. Woof. All right, so I don't think I'll do another one. That took a long time. I'll do another one in the next lesson set. Just probably refer you to this and just do it mechanically from now on. And just remember lesson set 23. I'll just keep saying that for a few lesson sets. Go to lesson set, the beginning of lesson set 23. I take more time with things. All right, so now 2 more problems. Get to the other side of the board. There we go, back here. All right, so it looks like I'm talking Arcsin over here right now. It's really important, and this is what I try to develop from the Algebra 1 to Trig class, which I do at all levels. I teach the same course at Algebra 1, Algebra 2, and Trig. It's just Algebra 2 we get to go farther, and Trig we a little farther. Okay, it's nice if you get a hold of somebody at the Algebra 1 level and work with the zeros and one videos and start there and move on. So what I've noticed from my teaching experience is I have to really ask the question, and I'm going to ask you, do you know what that stands for? And do you know what that stands for? That is all about angles. This command has no meaning unless you're working with an angle. And an angle can be shown in two different ways. Most students are pretty familiar with 360 degrees, but have a hard time when things are in radius lengths. All right, so this is a radius length. And I think in grade school, it would have been nice if you put a string around a can and asked how many diameters does it take to go once around the circle. That's where pi comes from. All right, so 3.14 over here is pi, and how far did I go? 180 degrees. So if I said, what's the sine of 3.14? It's basically saying, what's the sine at 180 degrees? Notice I said basically because, you know, you get more accuracy with putting in more of the decimals. Okay, so if you're not sure how to do, let's say I'll just pick a random one. Cosine of 11 pi over 3. All right, what's the answer to that? A half. Now, how did I do that? Well, 2 pi, right, pi over 3, and I'll only do this once here, because you can go to the lesson sets and practice this, the Algebra 1 to Trig lesson set. I'm breaking it up into 3 parts, which means there's 6 parts altogether, which means 12 pi over 3. 6 pi means I went around 3 times. Well, 11 pi over 3 is just 1 less. And I work every day with the 30, 60, 90s, and 45, 45s. That's a half. That's what that width is. You want to be able to do those in your head. You know, 2, 3 seconds, bang, you know that. And if you're not there, then the trig that comes at you in calculus is hard. The calculus isn't so bad once you understand the concepts, which does take a months to understand integration and differentiation. Okay, but if you're struggling with the trig, then go back and get some practice with those early. Go to the playlist, the trig playlist, and definitely look at Introduction to the Unit Circle. And what is a radian? All right, enough. So this is the inverse. Well, what's the inverse? I never said what y equals. Y equals a ratio. We just gave you one a second ago. Cosine of 11 pi over 3 equals the ratio 1 to 2. So if this is angle to ratio, then what's that unit of measurement? You've got to have ratios. They better be between 1 and -1 because that's the range of the sine function. These are angles. So now, knowing that, we can draw a picture, we can work with Pythagoras, and we can derive the derivative of the arcsine. So first step is to solve for x. X equals the sine of y. That means that's an angle. So I drew an angle and I called it y. And I know that this sine is opposite over hypotenuse, so it's really x over 1. And now I can use implicit differentiation. 1 times the change in x is equal to the cosine of the angle y times the change in y. That's why radians work so well. Okay, if cosine of y, let's say y was 3, y was 3 means that I'm just that far away from 3.14. So when I said y is 3, I didn't say degrees, which meant that that's an angle. 3 units is all the way over there. And I'm spending so much time on that because I know that's where students struggled when they came into my calculus class. I'm like, okay, they don't know this. Didn't happen in their last class. We got to talk about it, but we can't talk about it immensely because it's a calculus class, so you got to kind of do it at the same time. So I'll keep saying what a radian is, and maybe the lights will go on. Maybe you go, I get that now, because I've heard that many times in a classroom. And that's what we want to hear. Oh, I get that now. So implicit differentiation, we've shown these work numerically in earlier lesson sets, not with trig. It's harder to show with trig, but we've shown the polynomial relationships and why they work. In fact, the related rates did one yesterday in the last lesson set. So if I want to get dy dx, I got to bring the dx to the right. I got to divide by the multiplication becomes division, and I get 1 over the cosine of y. Well, I can find that with this picture. We've done enough to know that this is the square root of 1 minus x squared. We did that so much in the Algebra 1 to trig videos. Why? So you can handle something like this. All right, and so what do I have? What is the cosine? This length divided by the hypotenuse. So therefore, what is, and I'm going to erase this now, what is the cosine? It's the square root of 1 minus x squared. So you memorize it. And so what would the derivative of the arcsine of, maybe you'll intuitively know this, arcsine of x squared? Well, it's 1 over the square root of 1 minus x squared squared times the derivative of x squared, which is 2x, and we don't write it that way. We basically say, when we do these, the derivative of what's inside over the square root of 1 minus what's inside squared. That's the mechanics. Sounds very similar to taking this derivative of the square root of x, I hope. Hope it sounds very similar. So what is the derivative of arcsine of f of x? F prime of x, I'm going right to the shortcut now, f prime of x in the numerator, the square root of 1 minus whatever f of x is, whatever the calculation is, remember to square it. And now we have another problem in front of us that we can put on the lesson set so that we can put it in long-term memory. And how many of those do you have to do? I think if you do one every day and you see it 4 days in a row, I think it's in your pocket. And I think if we continue doing it for another 5 or 6 lesson sets, it's in your pocket for longer. Okay. Now let's go over here to the inverse problem. So let me get some space, the final frontier out of the area here. There we go. Now that's kind of on its own merits. Let's look at it. So we got a function. F of a gets us b. F prime of a gets us m. I wrote m thinking a slope of x plus b, m slope. So inverse of f of a equals b is g of b equals a. And if I want the relationship here, the derivative at b, it's 1 over m. It's reciprocal. And I showed that a couple of times in earlier lesson sets with x squared. So what's the derivative of x squared? 2x. So at x equals 3, f of 3 equals 9. And f prime of 3 equals 6. Then over here, g of 9 should get me 3. And g prime of 9 should get me 1/6. And I've shown, put a 9 in. There you go. So at x squared, we have a tangent over here going up like that. Square root of x. Over here, we got one going up like that. And they're reciprocals. All right, so how about if I give you f of x equals x cubed plus 4x, and I want to find g prime of 145. G prime of 145. And since I've already done this in lesson sets 4 or 5 times, they'll just become mechanical practices going forward. But I wanted to highlight it because at the end of the term, if something isn't understood, it's time to do 2 or 3 problems like it, 2 or 3. And then if 3 weeks later it's still struggling for you, then we do 5 or 6 in a row. And after that, we give up. No, I'm just kidding. I'm kidding. By then, usually people, I get it now. All right. So what gets me to 145? Well, let's throw 5 in. That gets me close, right? 125 plus 20. So what I'm basically saying is f of 5 is equal to 125. And we can find f prime of x. F prime of x is 3x squared plus 4. So I know what f prime of 5 is. F prime of 5 is, drop a 5 in, 75 plus 4, 79. All right, so what is g of 125? 5. And what is g prime of 125? 1 over 79. That's what we're practicing. And I didn't mention it before, but how do you find slope? y2 minus y1 over x2 minus x1, which is what we're doing with dx. We're looking at y2 9.01 minus 9 over 0.01 minus 0, something like that. Oh, God. And how do you find inverses? Algebra 1, what's usually what something says initially, change your x's and your y's. Well, if I change my x's and my y's here, let's get that. Well, I ask you to multiply these, and you tell me what you get. So that's that. All right, so that's a little bit slower chat, a little bit of practice while chatting. And now the next lesson set might do those 3 problems first. Probably will start with those from now on first and work our way back to what's the derivative of y equals x squared. And why is it 2x? How come? Maybe, when I ask that, maybe, just maybe, and this would be very hopeful, why is it that 2x is the derivative of x squared? Because when you draw a square, and you look at the area, putting a layer, that length is x, and that layer's length is x, and if we give those lengths a little bit of width, then we get the change in area, which is the heavy dark part of the marker that I'm putting on the board right now, and I get x dx plus x dx is the change in the area, and if I factor out dx, it looks like it's 2x dx. It's dx times x plus x. Okay, so dy over here, why I did that, I knew I was going to be talking about x's, so if I divide by dx, 2x. Now, why did I take the time to do that? Concepts take time. That's been introduced throughout the 23 lesson sets now. But that doesn't mean each student picks it up on day 1. Very rarely. Right? Very rarely. But if you keep talking about something, oh, I get that now. That's what we're hoping for. Some conceptual awareness. All right, I'm ranting again. Get me the heck off here. Bye-bye.